Okay, in this video we'll discuss an issue related to interfacing with I/O, specifically switch bouncing, and ways that we can deal with this issue. Okay, so ideally switches would look something like this. So when the switch is open, there's no current flowing, and we see a digital 0, and when the switch is closed, we see a digital 1. In reality, for many switches, when they are activated, they may switch many times between 0 and 1, and we call this switch bouncing. This is a particularly tough problem for push-button style switches that we have on our development boards and many systems use. And so this is entirely a mechanical or physical artifact of the system. When we push this button down, there's some intermediate contact, and the signal that the system sees is actually oscillating for a short period of time. In the case of this particular switch, looking at the data, we see it has a 10 millisecond bounce time. So when we push that switch, or that push button, we see for a short period of time, the signal actually going from low to high. And the same thing happens when we take our finger off of the switch, we see this switch bouncing effect. Now there are different ways that we can deal with this, and you can probably guess one way is with software. We could just take the average or wait a given amount of time that we expect the bouncing to occur till we say that actually the switch has either been activated or deactivated. And then we update the display or the output accordingly after our expected delay in the key bounce. We can also mitigate this problem in hardware. But before we get into the hardware solutions, let's first look at how we typically connect switches to the I/O of our computer. So this is a standard circuit for connecting a single switch, such as our push button, to the I/O in our system. So one end of our switch is connected into the I/O of the microcontroller. And we also use a single resistor called a pull-up resistor connected to the high voltage at one end, as well as the input into our microcontroller. And the other end of the switch then is connected to ground. The purpose of this resistor is to ensure that even when the switch is not pushed or activated, we still have either a high or low voltage at our input pin, ensuring that our pins are not floating. And you'll learn more about this when you interface logic in 329. So for this circuit, when the switch is open, current flows into the microcontroller pin, and I'm going to see a high voltage. But when the switch is closed, we see a low voltage in my input pin. Okay, so then one way that we can protect against switch bouncing in hardware is to create a simple RC circuit. We'll put a capacitor in parallel with our switch. You may have seen in your previous courses how an RC circuit can be used as a low-pass filter, filtering out high-frequency noises, which is exactly what we want with these switch bouncing characteristics. Modern systems typically use something called a Schmitt trigger to debounce inputs, which is basically an RC circuit, but also has an output buffer circuit with some hysteresis built into it. So to summarize, when we press certain types of switches, including those push buttons, they see some bouncing, some oscillations, where it switches between 0 and 1 frequently until it eventually settles. Ideally, we would like to see something like this with our switch, but applying our debouncing techniques, we can still see a clean transition from 0 to 1, albeit with some delay. For our interrupt signals, which we want to generate to our microcontroller via the button, we also want to ensure that the interrupt signal goes only high for one clock cycle. This is called a one-shot, rather than staying high for several hundreds or thousands of clock cycles. And so this is what the debounce one-shot module is doing. It's a finite state machine that at the front end is going to ensure that the signal has actually gone from low to high, the debouncing. And then once the signal has gone low, the debounce one-shot module will, after some delay, give a single cycle with the output high and then back to low. Note that with our debounce one-shot module in the auto wrapper, this could be somewhere around 100 cycles later from the point where you actually push the switch. Okay, so just a couple of final notes here. The actual processing of our interrupts, those interrupt service routines, is relatively fast compared to the mechanical activation of the switches. Our processors are running at 50 megahertz on the Basis 3 boards, and the switches themselves could bounce for up to 50 milliseconds. So when using the button to trigger interrupts to our processor, we have to be careful because one button press on the board could actually result in many interrupts being generated to the board. And so this is what the logic for debouncing solves. We also have to be careful that the switch could still be activated after we finish processing an interrupt, triggering additional interrupts. And this is fixed with the one-shot logic within the module.